Welcome to the Longevity Papers podcast, the show that filters the noise so you, the biotech researcher, can focus only on the signal.
Our mission is singular and, it remains consistent. We're here to track down work that is truly transformative.
We're looking for those paradigm shifts, right? The discoveries that make you change your entire model.
Exactly. The stuff that has a non-trivial shot at enabling a 10-plus year lifespan extension in humans. Everything else, the excellent execution, the incremental wins, we acknowledge it, of course, but we just don't prioritize it. We have to keep our eyes on that high bar.
Absolutely. And let's be transparent right up front. Our assessment for this period, covering November 17th to November 30th, 2025, well, it was generally below that transformative threshold we set.
It was. We looked at, 105 papers in this data dump?
105. And the vast majority fell into categories that are, look, they're solid incremental science, but they're not the breakthrough we're hunting for.
And that's just the reality of the field some weeks. It's high volume, but a low yield for true novelty. We saw the usual suspects taking up a lot of space.
Like the microbiota papers.
Yeah, that whole cluster. I mean, they're scientifically valid. They'll find a specific exopolysaccharide or a particular odorobacter species, but it doesn't fundamentally change the therapeutic strategy. We already know gut modulation affects aging.
Right, these papers are just filling in the biochemical detail.
Exactly. Refinements.
And what about the senescence work? Some of that looked really well executed.
Oh, exceptionally well executed. New senolytics, advances in localized stem cell treatments, even some CAR-T stuff.
Yeah.
The science is incredible. But the core mechanism killing senescent cells, it's a known quantity. This is translational execution. You're taking a lever we already know about and just making it safer or more specific. And that's critically important for clinical goals, don't get me wrong.
But it doesn't expand the list of targets.
It does not. It's refinement, not discovery.
Okay, so we also saw that that endless stream of papers on things like exercise mimetics or dietary compounds.
Yeah, we dismiss those pretty quickly. They're useful for basic health span, no doubt.
Yeah.
But the gains are just marginal. You rarely see them exceed 10 or 20% lifespan extension, even in a mouse model.
And that performance just doesn't meet our criteria for a 10-year human goal.
Not even close.
And the last category, the biomarker papers.
Ah, yes. The new clocks, the proteomics, the epigenetic signatures, they're essential tools. I mean, they refine how we measure aging.
But measurement isn't mechanism.
Exactly. They tell us how fast the clock is ticking, but they don't give us a new druggable point of intervention in the process itself.
So after culling that field of 105 papers, we're left with a different kind of focus for today.
Right. Since there wasn't a single, epoch-defining mechanistic breakthrough, we're pivoting. Today is about 3 papers that stand out for other reasons.
Not for a new target necessarily, but for genuine methodological novelty.
Or for mapping a highly specific therapeutic axis with incredible detail.
Or for providing an invaluable resource that's going to underpin future work.
We're looking at the tools, the maps, and the blueprints that, collectively push the whole field forward and force us to ask better questions.
Specifically, we're covering an AI-driven discovery paradigm, a deep dive into RNA splicing and muscle failure, and a massive new aging atlas in the rhesus macaque.
So before we jump into those, I think we need to spend a moment on that fundamental question. What do we even mean by true novelty? How do we define that threshold for a 10-year gain?
It's a crucial distinction, isn't it? Incremental work, as we said, is about refining known pathways, finding a slightly better mTORC1 inhibitor or a new upstream regulator of AMPK.
It's necessary science, but it operates within a landscape that's already well-trodden.
Right. True mechanistic novelty, on the other hand, defines a new root cause of aging. It introduces a concept that we hadn't previously linked to that system-level decline.
It reveals a hidden lever. And this is where we should probably acknowledge the one paper that came closest to clearing that bar this period.
We decided to hold it over, right? Because the systemic data just isn't there yet.
Exactly.
Yeah.
But we have to use it as our benchmark for what novelty looks like.
You're talking about paper, #74. Targeting ROA nuclear mechanoactivity rejuvenates aged hematopoietic stem cells.
That's the one. From Eva Mejia Ramirez and her colleagues, published in Nature Aging on November 25th. It's just a phenomenal piece of work on hematopoietic stem cells, or HSCs.
And that's so critical for immune resilience, for blood renewal.
Absolutely. And this paper contains genuine novelty because it links a physical process mechanotransduction directly to the molecular machinery of aging and stem cells.
Okay, let's really unpack that mechanism because it's a beautiful piece of systems biology.
It is. They didn't just target ROA, They zoomed in on an intrinsic ROA-dependent axis driven specifically by, well, by the pathological accumulation of nuclear envelope tension in old HSCs.
So the nucleus itself is getting physically strained as the cell ages.
Precisely. The strain on that membrane, the barrier that houses the genome, it acts as a primary sensor of aging. This tension induces the translocation of a key enzyme, PCPLA2.
And that enzyme is critical because why?
Because PCPLA2 then cell intrinsically hyperactivates ROOA. It's this novel, tightly controlled feedback loop where accumulated physical damage directly triggers a specific signaling cascade inside the nucleus.
And the downstream effect of that hyperactive ROA is basically genomic chaos.
Yeah, cascade disaster. They found it degrades chromatin structure, causing a loss of that protective heterochromatin marker, H3K9AME2.
And losing H3K92 is catastrophic because it's like a defense failure.
It's total defense failure.
Right.
You lose that tight heterochromatin, and these retrotransposons, these sort of ancient viral DNA fragments in our genome, they wake up.
Which causes genomic instability and immune response. The cell is fighting itself.
A losing battle against its own genome. And the intervention is so clean, you pharmacologically inhibit ROOA, and it restores the nuclear homeostasis, recovers those crucial H3K9ME2 marks, and functionally restores the regenerative capacity of these old stem cells in vivo.
A complete reversal.
It's phenomenal. It validates mechanotransduction as a major targetable aging axis. It's the first time we've seen this specific pathway tension to PCPLA2 to ROA mapped as a primary driver in stem cell aging. That's true novelty.
So what? Hold it. The mechanism is new, the target is clean, the outcome is restorative. Why not focus the whole deep dive on this?
Because for our audience, for people planning decade-scale therapeutic deployment, you have to be systemically minded. The effect is HSC-specific. They've restored one crucial cell type. Our analysis suggests that even in a best-case scenario, the systemic health span gain is maybe 2 to 4 years. That's great, but it's not the 10-plus-year goal that justifies a multi-billion-dollar platform investment.
So the big questions are still unanswered. Does this mechanism drive aging in other tissues, in the gut, in muscle?
Exactly. Is nuclear envelope tension the initiating cause everywhere, or just a consequence in these specific cells? We need systemic longevity studies, broader tissue mapping, data that isn't there yet.
It's the blueprint for the next discovery, but it's not the finished product.
That's a perfect way to put it. It's a crucial benchmark for novelty, but we hold it until we see that system-level data.
Okay, so since we're holding that blueprint, it seems like we should pivot to the next generation of discovery methodology itself, which brings us to AI agents.
Exactly. How we use the data we already have.
You know, when we talk about finding new interventions, the traditional method is just so slow. It's also blind to context. It just fails to leverage the mountain of historical data we already have.
Which is why paper #41 represents such a genuine shift in the discovery paradigm.
This is autonomous AI agents discover aging interventions from millions of molecular profiles.
Yep. By Ying, Kashkovsky, Moldokazayev, and their colleagues from Brigham and Women's and Harvard Med. It was published on bioRxiv, that's BIORXIV, or bioRxiv, on November 20th. And it's really a methodological statement.
The novelty here is explicitly not the molecule they found.
No, it's the sheer scale of the approach. They shifted how we look for candidates by leveraging what a lot of people see as a data graveyard. Decades of public molecular data from labs all over the world.
Just think about that. All these compounds tested for cancer, for metabolic disease, but the aging phenotype was never the focus.
Right. It's a goldmine of longevity information, but we just lacked an automated way to analyze it all through the lens of aging.
And that's where the clock-based agent comes in.
It systematically reanalyzed a staggering 43,602 intervention control comparisons from public databases.
43,000. That is a haystack the size of a mountain. How on earth did the original investigators miss 500 potential interventions? What was this agent looking for that we as humans were just blind to?
The blindness was systemic. The original investigators were looking at 1 or 2 target genes. The clock-based agent. It used an integrated approach. It didn't rely on one metric. It integrated predictions from over 40 established aging clocks.
Epigenetic, transcriptomic, all of them.
All of them. To determine the cumulative system-wide effect, it was measuring system resilience, not just target engagement.
So it found over 500 interventions that significantly reduce biological age. Effects that were just totally missed. That's the ultimate data archaeology project.
And for validation, they followed up on one of their top candidates, Uabane.
A well-known cardiac glycoside. And the follow-up in aged mice was solid. Reduced frailty, decreased neuroinflammation, improved cardiac function.
All good health span improvements. But now, here's our skeptical analysis.
Right.
The methodology is a genuine, reproducible paradigm. If you're starting a biotech and need 500 candidates to triage, this is the tool. It dramatically lowers the bar for discovery.
But the target they found, uavane, is strictly incremental. Its effects are modest, and its relevance for that 10-year lifespan gain is, well, it's highly uncertain.
The paper even says it converges on canonical pathways, AMPK, MTRRC1 FOXO. The agent validates known biology. It's a new key for an old lock, but not a new lock.
An iterative win.
Exactly. But the truly profound insight here isn't the molecule. It's the large-scale, fundamental patterns that you can only see with an analysis at this scale. This forces us to reevaluate our foundational therapeutic dogma.
And two patterns really stand out. The first one is a bit depressing.
It is. Significantly more interventions accelerate aging than decelerate it. Intervention is inherently risky.
But the second finding, the one that demands some real philosophical exploration,
Is that loss-of-function genetic strategies systematically outperform gain-of-function strategies in decelerating aging.
and this is critical. I mean, for decades, so much of neuroscience has been about activation-boosting protective pathways.
We look for genes that, when you overexpress them, extend lifespan. We try to boost sirtuin activity. This AI agent, looking at massive mammalian data, suggests the opposite is true.
It implies that aging in mammals is less about a failure to express good stuff that needs boosting.
And more about the pathological, age-dependent accumulation of bad stuff that needs to be shut down. It suggests aging is driven more by accumulated noise and breaking failures, like that ROA hyperactivation we just talked about, than engine problems.
So should we fundamentally shift our R&D? Move away from looking for activators, the fuel, and focus on finding highly specific inhibitors, the brakes.
It absolutely challenges the axes that underpin some of the biggest companies in this space. I mean, look at our most successful interventions so far. Rapamycin, metformin. They're largely inhibitory.
They function as loss-of-function mimetics.
Right. This analysis strongly suggests that inhibition, shutting down a toxic age-dependent pathway, is just systematically more effective in the complex mammalian context than trying to boost a protective one.
So that opens up a huge question. If we're hunting for loss-of-function targets, well, that often means a more challenging therapeutic window, right? You're shutting down an active process. Does the agent give us any guidance on which pathways are the best to inhibit?
It validates that pathways related to chronic inflammation, DNA repair failure, and aberrant metabolic signaling are the most sensitive to loss-of-function strategies. It doesn't give you the single magic bullet.
But it tells us how to approach our hypothesis testing. If you have two pathways to choose from, one needing activation and one needing inhibition.
This massive data set biases us heavily toward the inhibitory approach for maximum effect on biological age.
So Clockbase is a methodological breakthrough. It accelerates triage, validates mechanisms, but its most powerful contribution is revealing this meta pattern about loss of function, which forces us all to revisit our core assumptions.
Absolutely. So moving from the new tools of discovery to a very specific molecular mechanism, paper hashtag 22 gives us a classic example of just exceptional, detailed mechanistic mapping.
And it's in a super relevant system, muscle regeneration failure.
This is TGF SMAD3 signaling restores cell-autonomous SRSF1-mediated splicing of fibronectin in aged skeletal muscle stem cells. It comes from Hugo Liu and colleagues at the Université de Sherbrooke in Canada, published in Nature Communications. It's a masterclass in coherence.
So the core aging problem they're tackling is the loss of regenerative capacity in aging skeletal muscle stem cells, or MOSCs.
Right. In old muscle, the niche, the environment, is compromised. And it's because the MOSCs can't properly produce key components, specifically certain variants of fibronectin.
And what's so fascinating is how they mapped the entire upstream regulatory axis. It's not a general problem.
No, it's a very specific defect. It starts with the TGF1 SMAD3 signaling cascade, which controls the promoter of a key RNA splicing factor, SORSF1.
And splicing dysregulation is really emerging as a core axis of aging, isn't it? When the cell can't edit the mRNA instructions properly, it makes junk proteins.
Exactly. And here they zeroed in on XRSF1, controlling the splicing of a specific fibronectin variant that contains the EDB extra domain, the EDB plus FN isoform.
And losing that specific isoform in aged muscle stem cells is the key failure point.
It is. It's crucial for facilitating stem cell proliferation through integrin signaling. Without that specific molecular flag, the monocies can't properly sense their environment and initiate the repair program. They lose the signal they need to activate.
And the fix they developed is just as precise.
Right. TGF-1 activation, the upstream signal, during a defined acute regeneration interval, restores that ADB plus FN splicing and improves muscle repair in old mice. It's solid, specific, and actionable in a targeted scenario.
That level of detail is why the paper is so valuable. It reinforces that RNA processing is a system-level vulnerability in aging, and this paper gives us a precise blueprint in one vital tissue.
However, this is where the skepticism is paramount for our audience. While the mechanism is solid, the therapeutic liver TGF-1 activation comes with significant baggage.
A ton of baggage. Systemic TGF signaling is notorious. It's often associated with fibrosis, right? Scar tissue, organ stiffness.
Exactly. In the kidney, the lung, the heart. The potential risk profile for chronic systemic use in an elderly population who already have elevated fibrosis risk is substantial. I mean, it could be aggressively counterproductive for longevity.
So it sounds like a target we should just immediately dismiss for our 10-year goal. But if the underlying failure is so specifically mapped, shouldn't we focus on the delivery challenge? The intervention only worked for acute regeneration.
That is the critical distinction. If it only works during acute injury, the therapeutic window is confined. The goal shifts from systemic lifespan extension to localized pulse restoration.
So you could use AAVs or hydrogels to deliver the signal only to the damaged muscle for a short period.
Potentially, yeah, a near-term win for elderly rehabilitation. But that doesn't solve the core longevity problem.
Right. We need to know if the stem cells are failing before an injury. The authors mapped the acute failure, but they didn't answer the core question. Does restoring this splicing improve long-term muscle aging trajectories independent of an injury?
That's the missing data. The core biology is sound splicing dysregulation drives tissue-specific failure. The therapeutic path, TGF-1, is incrementally useful for localized recovery, but its known risks mean it does not clear the bar for a transformative longevity intervention without massive safety work.
It's a perfect candidate for a 2-year health span gain, but not the decade-scale extension we're looking for.
It reinforces that even the most elegant mechanism can be limited by the pharmacology of its upstream regulator.
Okay, so if that was about a hyper-specific failure, this final paper is about system-level mapping. It's a foundational resource that could shape our hypotheses for the next decade.
It really could. You're talking about paper #70, a multi-omics molecular landscape of 30 tissues in aging female rhesus macaque.
This resource, from Gonghua Li and colleagues at the Kunming Institute of Zoology, published in Nature Methods, it's just immensely valuable.
It's the first truly comprehensive, high-resolution multi-omics allotranscriptome, proteome, metabolome across 30 distinct tissues in non-human primates.
For biotech researchers, this is gold. Macaques are our closest evolutionary model for studying systemic aging before we jump into humans.
The logistics alone are staggering. 17 female macaques, ages 3 to 27, spanning the full adult lifespan across 30 tissues at once. It's a massive effort to create a baseline for primate aging.
And the value proposition is just so clear. We can now test every hypothesis we generate from mice, from that AI agent, against the complexity of a primate system.
And it does confirm some things we expected, like general increases in inflammation across tissues, so we know we're not completely off base.
But the key structural finding, the insight that drives future hypotheses, it's the observed asynchronicity of aging.
Yes. The molecular clock does not tick at the same rate everywhere. They were able to classify all 30 tissues into 2 distinct types based on their molecular aging profiles.
And this is so crucial for therapeutic targeting. If aging is asynchronous, we shouldn't target every tissue equally.
We should focus on the tissues that are falling apart the fastest, the ones that seem to be driving the overall systemic decline.
So what was the molecular feature that defined that rapid aging group? This is the core insight.
The tissues showing more pronounced aging were systematically associated with decreased mRNA translation efficiency.
So this links system-level aging in primates directly to the fundamental cellular machinery for making proteins.
It strongly suggests that translational capacity, the ability to efficiently make new, high-quality proteins, is a core system-level aging driver in non-human primates. It's not just about which genes are on, it's about the fidelity and speed of carrying out those instructions.
And this aligns so well with prior work, right? We've seen hints of this with ribosomal quality control defects causing premature aging. This macaque data reinforces that translation efficiency is likely a central regulator of tissue aging rates in long-lived mammals.
Absolutely. But we have to stress the limitation here. This paper is purely descriptive.
It identifies the pattern, but it lacks any interventional proof.
Exactly. There's no evidence yet that correcting this decline extends lifespan. It opens a huge area for hypothesis testing, but it doesn't give us the therapeutic blueprint yet.
What it does provide is the map for our next trials. We can now stratify tissues. We can ask which specific tissues, the liver, a subset of immune cells, show the steepest decline. Those are the ones to prioritize.
Imagine the difference that makes. Instead of the shotgun approach, we can use this atlas to identify the rate-limiting step for the whole organism. If the liver shows a huge deficit, you target the liver's translational machinery first.
This resource really solidifies translational capacity as a critical system-level axis, right alongside MTOR and mitochondrial function.
It does. And the critical follow-up question is now defined by this paper. If we target the factors that restore translation efficiency, which tissues should we aim for, and would it yield the systemic longevity extension we're looking for? This atlas provides the foundation for designing those studies.
The resource value here is just huge. I suspect future papers using this atlas for validation will probably dominate the conversation in the next year.
No doubt. Everyone's going to be rushing to match their targets against this definitive primate baseline.
So this period, while it was lacking that single transformative breakthrough, it was really crucial for providing the foundation we need for the next generation of discovery.
I think so. Let's just quickly recap the three thematic areas from this period.
First, we saw that critical breakthrough in methodology, the clock-based AI agent. It showed us how to leverage decades of existing data.
And, critically, revealed that meta-patterns suggesting loss-of-function strategies systematically outperform gain-of-function strategies in decelerating biological age.
Second, we looked at that highly detailed mechanistic work on splicing dysregulation in muscle. Paper #22 mapped a specific cause of regenerative failure.
But we noted that the therapeutic lever, TGF-1 activation, is incremental and carries significant chronic safety risks, pushing us toward localized solutions.
And finally, we gained a crucial systemic resource, that multi-omics atlas of aging macaques.
Right, a descriptive work that's essential because it identified aging as highly asynchronous and linked the worst aging phenotypes to decreased mRNA translation efficiency. It strengthens the case for translational capacity as a core aging driver in primates.
So our overall assessment remains. This was a resource and method-focused period, not a breakthrough period for immediate decade-scale deployment. The work is foundational, but the heavy lifting is still ahead.
Which brings us to a final provocative thought for you, the researcher, as you think about this new avenue opened by the Macaque Atlas.
We know declining mRNA translation efficiency drives accelerated aging in key tissues, but we have to ask a fundamental question about how we should intervene.
Is this age-associated loss of efficiency primarily due to accumulated damage in the machinery itself? You know, a pure ribosomopathy where things are just broken and we must fix them?
Or is it the opposite?
Or is this decline a protective, regulated energy-saving mechanism, a homeostatic response to slow things down, prolong survival, something that shouldn't be fully reversed?
Because if the cell is intentionally down-regulating translation to conserve resources, turning that break off completely might lead to metabolic exhaustion or who knows what.
The answer determines the entire safety profile of any resulting therapeutic. If it's pure damage, restore it to youthful levels.
But if it's a regulated break, we have to be much more careful. Maybe we only partially relieve it, or find a way to maintain translational fidelity without just cranking up the efficiency.
It's that classic longevity trade-off. High proliferation versus long-term resilience. And that's the critical risk assessment required before we move this into the clinic.
Something fundamental to mull over.
For sure. Until our next review.
Thank you for tuning in to Longevity Papers. We'll be back soon with the next review of the newest data that matters most to the field.